All right, guys. So I know you've read the section, right? I know you have. Of course you have. But I just want to point out a couple important things about the section, and then I want to just do examples and show you kind of the notation that I want to see, because it's hard for me to sometimes grade these because you're doing it all by hand, and if it's consistent notation, it's easier for me to follow your work. And then hopefully it'll help you kind of keep your work organized as well. All right, so let's just point out a couple important things about this section before we move on. So just like we talked about in 1.1, we're dealing with linear systems. So if I have a system, and you saw this like this, you know, this wouldn't be too hard to solve on our own, but we're going to have more variables in this. We're going to have bigger systems, and we saw that on the fun sheet. It was kind of hard to solve some of those 3x3 by hand. So matrix is going to help us do that. So just some terminology stuff. If I take this side of my linear system and I consider only the coefficients, which really only the coefficients are the ones that are going to be manipulated when I do the operations that I'm allowed to do, right? What are the operations I'm allowed to do? Interchange any two equations, multiply an equation by any non-zero real number, and then add and subtract equations to each other. Well, when I do all of those things, the only thing that really changes are the coefficients, because when you multiply by something, you multiply the coefficients. So that's what leads so well to using matrices, because these matrices that we use are going to be, this is what we call, hence the name, a matrix of coefficients, okay? And then now, of course, the other side of this system is quite important, right? Those numbers obviously determine a lot of things about what our solution set will be. And so we consider these numbers right here. I can put these into their own matrix, and I'm going to actually, this is just 7, 6, but because it only has one column in it, we call this a vector. So those of you in Calc 3, half the class, this is different. This is different than in Calc 3. We call it a vector because it has a single column. That's all. That's it. That's a vector, okay? So that's our matrix of coefficients. That's our vector. I thought they did a good job of showing, if you look at table 1.1 in the book, they do a good job of showing why matrices can be useful to store data. So, you know, they talk about the number and type of ice cream that is sold every day. And while in table form, that can be kind of hard to work with, it's quite useful in a matrix. So the general form then for a matrix, and we saw this before, but I want to write it down again, is if I have a system like this, A11, X1, remember it's not A11, it's A11, A12, oh, let's put a variable in there, Sarah, X2 plus dot, 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 thank goodness for the dot, dot, dots, A sub 1n, X sub n equals B1, right? Here this would be A sub 2, 1, the first number indicates the row we're on, the second number indicates the column. Dot, 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 plus A sub 2 n X sub n equals B sub 2, dot, dot, dot. Let's say we have m rows. So this would be m1, x1, plus dot, 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 A sub m2. I know we wrote this down already, but you know when you write it down more, you remember it. So that's why we're doing it. A sub mn. Whoa, what did you just do there, Sarah? X sub n equals B sub m. Okay, so now I have this general form for a system, and now I can actually create a matrix. Now, I can create a coefficient matrix, and then I can create a vector that indicates kind of the solution side of my system. But what I'm going to do instead is put those together. So this is where we get something called the augmented matrix. So I would have A11, A12. Again, I'm only concerned with coefficients, A1n. So I'm going to make my coefficient matrix A21, A22, dot, 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 A2n, dot, dot. I don't know, I have to say the dot, dot, dots out loud for you. So M2, dot, 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 dot. And then we usually do a diagonal dot, dot, dot here, dot, 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 A sub mn. So there's my coefficient matrix, all my coefficients. And then what we're going to do, so we don't have to have a separate matrix or a separate vector, is we usually put a line right there. Sometimes you'll see that line there, sometimes you won't. So we need to kind of know what we're dealing with. Are we dealing with just a coefficient matrix, or are we dealing with something like this where we call this an augmented matrix? Okay, so when we're talking about an augmented matrix, what we mean by that is we're going to be including that last column of those solutions. When we talk about just a coefficient matrix, just like it sounds, we're only dealing with the coefficients. Obviously, I hope, kind of. All right, and so what are we going to use to, we're going to mess with this matrix, as you saw in the reading a little bit, to get it into our reduced row echelon form. And we're going to do that using Gaussian elimination, or that's the process of it. But before we can do that, we need a couple of things. So the important things we need, I don't know why I had you read when I'm just actually lecturing on all of this, are what we call, this is very, very important, we need the elementary row operations. These are the things that we are allowed to do to the matrix without changing the solution set. Okay, because remember now this matrix just, not models, but this matrix represents the linear system that we're solving. So remember what we could do with a linear system. Interchange any two equations, multiply an equation by a non-zero number, and add and subtract equations together. So elementary row operations, these are operations that can be carried out on a linear system. Okay, has to be linear. That's the name, linear algebra, without changing the solution set. Okay, so they'll be equivalent. So the matrix might look different, but they're equivalent matrices, and what we mean by equivalent matrices is they have the same solution set. So even though it looks different, we still are representing the same values for X, Y, Z, or whatever we're dealing with, okay? All right, so what are the elementary row operations that we could do? Number one, we can multiply any row. Now remember, I'm talking about rows now, because each row, recall, let's look at this really quick. I really want to point this out. Maybe I didn't really say that before, but if you look at this row right here, right, this row represents this equation right here, right? Where what do the columns represent one of these matrices? This column, these are all the coefficients for x1. These are all the coefficients for x2. These are all the coefficients for xn. But this row of the matrix corresponds to the first equation in my system, okay? So that's an important thing to understand. All right, so what can we do? I know I can multiply an equation as long as I do it on all sides, any non-zero number I want, and so I can do that. I can do that also to rows in a matrix, because again, those rows represent the equation. So what can I do? I can multiply a row by a non-zero constant, the whole row, including the augmented part, right? We must do the augmented part. Okay, so I can multiply a row by a non-zero constant, and that won't change the solution set. Okay, second one, I can add or subtract a multiple of one row with another. Okay, we know we can do that, right? So I can multiply one row by 2 and add it to the second row and then put it maybe back into the second row, right? But then that first row would just stay the same. Well, I guess you can multiply by 2 later, but okay. And then the third one, we can interchange any two rows. So these are the three things we can do, okay, without changing the solution set. You shall not do anything more than that. You'll have to use all of them, but you don't want to do anything more than that, okay? So that's what we mean by elementary row operations. All right, so the process of getting a matrix, as you saw, into this kind of triangular matrix is something that we call Gaussian elimination. So let's write that down, and then I promise we're going to do some examples. And I want to write this down, but then I just really want to do examples, because that's going to show you why it's going to work. That's going to be the best way to do this. I can talk about this all I want, but if I just show you, that's going to help you see why this process worked. But Gaussian elimination, this is a method using elementary row operations. Did I call them elementary row operations up here? Oh yeah, I did. I don't know why I just like, I don't know. I don't remember writing elementary up there. Using elementary row operations to produce, we're just gonna call it, we'll just put little quotations, a triangular matrix. We'll have definitions for that later, but a triangular matrix with zeros in the bottom left corner. Okay, so once we do that, and again, I'm going to show you examples of this and it'll probably make more sense. Okay, once we have done that, got that into the zeros in that bottom corner, then back substitution may be used to solve the system. Back substitution can then be used to solve the system. And I'm going to do this with the 3x3. It's a little more interesting than a, sorry, when I say 3x3, I mean the 3x4, but I mean 3 unknowns and 3 equations. The 2 unknowns and 2 equations we could do with, it's just not maybe as interesting. So let's do an example. Okay, so let's solve this system using Gaussian elimination, and then we'll use some back substitution. Oops, computer's being a little bit lagging today. So let's see, did your book use, oh, it does use XYZs. We'll eventually stop using the XYZs, but let's say we have x plus 2y plus z equals 3. I guess it doesn't matter because we're going to put this in a matrix, right? So who cares? Minus 3z equals -1, and 2x plus 3y plus z equals 4. Okay, so when you're doing these, let's first make our augmented matrix. So I'm going to make my augmented matrix. I usually go by, well, I shouldn't say I usually, I feel like I do it differently every single time, but I'm going to just go by columns. So I have 1, 3, 2, 2, -1, 3, 1, -3, 1. And then I'm going to augment this with the vector 3, -1, 4. Okay, and so here's where you're going to tell me what you're going to do. So what I want to do to get this into Gaussian elimination is what they mean by a triangular matrix is I want this triangle right here. You can kind of see it. Oh, I just did that. I want those to all be zeros, okay? If those are all zeros, we'll see kind of what happens. That's going to be pretty cool. So for this to be 0, let's just kind of go down the line. What I'm first going to do is trying to get this 3 to become 0. Well, how would I do that? So I'm going to take 3 times row 1, okay, and I'm going to subtract row 2. And then I'm going to put it back into row 2. Okay, so this is where I am telling my reader, me, you're telling me what I'm doing. And this is the notation I would like to see. So I'm going to, again, multiply the top row by 3. Then I'm going to subtract row 2 from it. And then I'm going to put this into row 2. So notice that the only row that is going to change is row 2. So yes, I multiplied row 1 by 3, but I'm not going to keep it as 3. I'm only doing that to get that 0 there. So the first row is going to stay the same. 1, 2, 1, 3. All right, so let's see what happens when I multiply row 1 by 3 and subtract 2. I get a 0 here. That's good. Then I would have 6 minus a -1, which would be 7. And I would have 3 minus a -3, which would be 6. I don't have anyone here checking my arithmetic, so I hope I did it right. You should check me. So, okay, so I've done the second row, and I'm going to do 2 operations at once. Maybe I shouldn't. I'm going to do 2 operations at once, okay? You can do that if you would like. I'm fine with that. If I were to do this step by step and not like do 2 operations at once, I would put the third row and then I would put another arrow. But I can also say, okay, I did that one, and then what else am I going to do? I'm going to take 2 row 1, and I'm going to subtract row 3, and then I'm going to put that back into row 3. Okay, this right here is the notation that I want to see. Okay, So if I did that, now I'm going to go and I'm going to focus on row 1 and row 3, right? So if I multiply that by 2 and subtract, again, I get 0 here. That was the whole point. That's why you did it. 2 times 2 is 4, minus 3 is 1. 2 times 1, I'm at the third column here. 2 times 1 is 2, minus 1 is 1. And then 2 times 3 is 6, minus 4 is 2. So we're getting pretty close here to where we need to be. Okay. All right, so now let's look at how to get, my next step, right, is I need to get this 1 right here to become a 0. That's my goal, and then I will have it into that Gaussian elimination, into that form where I have zeros in the bottom left-hand corner of my matrix. Okay, so to do this, there are a couple things that we could do. You could multiply the second row, right, because I don't want to mess with, you don't want to use the first row and add it to the third row, because if we did that, you guys, then notice I would lose that 0 that I had just worked hard for right there. So you don't want to mess with the top row because that will change those zeros that you had just got. So what I want to deal with then is I'm going to be looking at how can I use this 7 or how can I use this 1 to make this a 0 where that 1 is. So what I'm going to do is I'm going to multiply the bottom row by 7. So I'm going to do 7R3. I'm going to subtract the second row from it, and then I'm putting it back into the third row. So that means the second row stays the same. Okay, so I'm going to have 1, 2, 1, 3. The top row I didn't do anything with. Second row stays the same, right? Because I'm going to do that elementary row operation to just change the third row. So if I multiply the bottom row by 7 and subtract the second row from it, I would get 0, right? Then I'd have 7 minus 6, which is 1. And I have 14 minus 10, which is 4. Okay. And now notice I have it in the form I want because I have these zeros right here in this kind of triangle. We'll talk about that in a moment. About kind of what we call that, but we're set. Now, why is this going to help us? Because remember that all of these rows, right, indicate that these are equations. So if I were to write the corresponding equation for each row, this would be x plus 2y plus z equals 3. The second row here would be 0 x's, right? So it'd be 7y plus 6z equals 10. And then the last row here, this is the winner right here, this is z equals 4. Okay, that's why we want that triangle, because then that bottom row is going to give us one of the solutions if we have a solution, right? What would happen if we didn't have a solution? Well, we'll just get some weird stuff going on here. Like if I had a 0 here, then that would say that 0 equals 4, which we know isn't true, right? That would tell us that that system's inconsistent. All right, so now we do what the idea of this back substitution, okay? Because what do we know? Sorry, 1 second. We know that z is equal to 4, so I'm going to just do that's why it's called back substitution. So I have 7y then plus what? 24 equals 10. So 7y equals a negative 14. So y equals negative 2. And now I can substitute that and z into that first equation there. We'll do that over here, I guess. All right, so I'd have x plus 2 times y is what? A negative 4, right? And then plus 10 equals 3. So I have x plus 6 equals 3. Subtract the 6, we get x equals negative 3. So what is our solution? This is a consistent system. A solution exists and it's unique. So we have negative 3, negative 2, and 4. All right, guys? Cool. Not too bad, right? Those are kind of fun. I like doing them, and it's easier, especially when you get like on the fun sheet. Some of those numbers were just not nice at all, and so this can be an easier way to do that. Really quick, a quick definition that is quite important. Well, I don't know if it's a definition, but I just want to kind of put terminology here. Two matrices are what we call row equivalent. Okay, so we'll use that terminology quite a bit. A row equivalent if one matrix is derived from the other using elementary row operations. Right? Why do we know? And another way that we can talk about two matrices being row equivalent is that they have the same solution set. These matrices have the same solution set. They represent systems that have the same solutions. Cool. All right. So if we look back up here, maybe if it'll let me go up here. So look at all the different matrices I have, right? I have 3 different matrices. I have this one, and this one. All 3 of these matrices are row equivalent. All right, cool. All right, so as you saw in the book, we went a little further from these, the Gaussian elimination to extend extending row operations, right? So the forms, not just having the zeros in the bottom left corner, but going further than that. And that's where we have these different types of forms for our matrix once we simplify it down to that. So for example, in our last one that we did, right, this matrix right here, well, we had a 1 there. Why don't we do another one? So we got kind of lucky that there was a 1 there when we had to solve for z. So a lot of times what is nice about this, what do I mean? This is getting a little convoluted, but this part right here, you don't necessarily have to have a 1 right there, right, for me to be able to back substitute. If that had been like, you know, 4 and then that was 16, I would still get z to be 4. So a lot of times it's nice to get a 1 right here, and sometimes it's even nice to get a 1 right here. And then to take it even further, what we sometimes like to do is get zeros right here. And that's what we call reduced row echelon form. So what I'm going to show you an example of getting it into reduced row echelon form, and then we'll talk about the different types of reduced row echelon form. Okay, so let's do an example where we get that matrix actually into reduced row echelon form, and then we're able to solve it pretty easily once we get it in. Well, not pretty easily. The solutions are just right there. Okay, so let's consider. Well, let's consider not doing this in orange. How about that? So I'm just going to find us one here that I want to do. Okay, so we're going to, oh my goodness. How about this example? Now I'm just going to kind of talk you through this. I know, well, you looked at the book and you looked at what RREF is, but let's do one of these. So remember, our goal here is to get 1s along the diagonal and 0s everywhere else. That's pretty much our goal. And we're going to see more complicated systems later on, like we won't actually see that until 1.7. But for right now, let's just do, we're just looking at ones that kind of behave nicely, right? That get into that form pretty easily. Okay, so this equals 5. Let me make sure I copied this down correctly or I'll be very, very sad. All right, so let's make our augmented matrix and then let's do elementary row operations to get this into even a I don't know, it's not really easier to do this. Once you get those zeros in the bottom left corner, I think back substitution is just as easy. But the thing is when we bring in the calculator is going to put it into that RREF form for us, and it's going to be really nice and easy to see the solutions. So we're going to practice putting it into that form. Okay, so I have 2, 1, -3, -3, 4, 1, 2, -1, -5, augmented with 2, 9, 5. Okay, so to get this into RREF form, I am shooting for this. Now, this is not always going to be the case. Sometimes you won't have a 1 in that bottom there, or sometimes you won't have something else going on, but I want to get it into this form. Now, why is this useful to get it into this form? Well, remember, that each row indicates that this is an equation, right? So look at what this is saying. This is saying x plus 0 y's plus 0 z's, which is just 0, equals whatever number this is going to be here, right? So my solution just pops out. This is my solution vector, just like that. I know once I get it into this form, I know what my solution is just by looking at it. I don't have to do any back substitution or anything like that. So the first step is I want to get a 1 in front in the upper left-hand corner. Well, I could do that. I could mess with this somehow, but do you notice that I already have a 1 right there? So why don't I just interchange those two rows? So I'm just going to interchange row 1 and row 2, and this is how I'm going to write it. So I'm going to interchange row 1 and row 2. The reason it's nice to get a 1 right there is because now I can get zeros underneath it. So what your goal is going to be is to get all zeros underneath, and then you can start eliminating zeros above things, okay? Oh, I see. I made a mistake. 1, 4, -1, 9, and then 2, I just copied that same thing because I was talking. What do you know? So this will be 2, -3, sorry about that, 2 and 2. Okay, so now my goal, I'm going to do operations to get zeros right here, okay? That's my goal. So I'm going to take 2 times row 1 minus row 2 and put it into row 2. I'm going to take 3 times row 1 and add it to row 3. Whoa. Row 3 and put it into row 3, okay? And again, this is the notation I want to see. So my top row stays the same. Okay, when I take 2 times the top row and add it to the second, or subtract it from the second row, I'm going to get 0, 11, -4. Let's see, 18 minus 2 is 16. So you can verify this. You can verify I'm wrong if you want. Hopefully I'm not. On the top row, I'm going to multiply by 3 and add it to the bottom row because I had -3 already. So that'll be 0, 13. -2, and I'm going to multiply that by 3. 27 plus 5 is 32. Let me check this. Hold on. All right, I think I have a small mistake right here. So if I multiply that by 3, this isn't going to make it too much better, but that'll be 8. The solution should be nice, but it's looking like this was one. I just picked it. It's not going to be the best thing ever, but we're going to get through it. It'll be all right. All right. So now we're going to have some fractions involved, and I think eventually it'll be okay. But we are going to have some fractions up until then. So usually what you want to do, now we could do a couple of things here. So remember, and I think I might try and do that. I want to get a 1 in this spot right here, right? And then I want a 0 everywhere else. But you really want to basically work with getting your zeros in your bottom and then working that way. But I think to be able to get a 0 in the bottom, well, I think we could do this. Let's go ahead and just get a 0 in that 13 spot right there. So what am I going to multiply by? I know this is going to be a little bit nuts, but I'm going to multiply. Let's multiply the second row by a -13/11, right? Times row 2. Add it to row 3, and then put it back into row 3, okay? Again, the top guy, I know this is a little bit cumbersome. I just grabbed this one. I knew it had a nice solution, so we'll see if we get that nice solution. So I'm going to leave the second row as is. And if you have some scratch paper or something, you might want to use it. So why did I multiply by -13/11? Because that gives me -13 here in where the 11 is, plus 13 is 0. That was the whole goal. I'm going to just do a little bit of side work. So -13/11 times a -4, right? And then what am I adding to it? Plus -8. Whoops. Let's move this over just a little bit. Maybe. Oh, sorry about that. Nope, I don't want any of that. Okay. Okay, sorry about that. My computer's not liking me. I haven't done a lecture in a while. I'm going to multiply this by 11/11 to get some nice numbers here, maybe. I don't know. I think I'm going to get on my calculator. Wouldn't that be easier? So 13 times 4. And then I'm going to subtract 88 from that. Okay, so we get a -36/11 right here. Oops. This is just going to make us appreciate having our calculators someday. And then let's look at that last one, the 16. So if I have a -13/11, times 16, right? And then what am I going to add to it plus that 32? That's this guy right here. Remember, I'm going to multiply that by 11 over 11. Okay, so negative 13 times 16. And then I'm going to add 32 to it. This will be fine. We get a negative 176 elevenths. But the nice thing here is, remember, I can multiply any row by whatever number I want. So what am I going to do right away? I'm going to go ahead and I'm going to clear this row, right? And I'm going to get rid of the 11s. And then here also I want a 1 in the second row right here. So I'm going to do two operations right now. I'm going to take 1/11 of row 2 and put it back into row 2. And then I'm going to go ahead and multiply the bottom row by a negative 11 times row 3 and put it back into row 3, just to get it kind of nice and see kind of what happens. I actually think we're going to get a pretty nice number there. Oh, maybe we're not. Let me see. Hold on, guys. I'm going to make sure. I think I made a little mistake here. Let me look. Okay, I found my mistake. Sorry about that. This should be 144. I forgot to multiply the 32 by 11. 144. This is going to be better. Okay, so top row I'm not doing anything with. That's going to be the same. Okay, here I'm going to divide by 11, so this will be 0, 1, negative 4 elevenths. That's all right. I'm not scared of fractions. 16 elevenths, right? And then on the bottom, I'm going to multiply by a negative 11, so I get 0, 0, 36. 144. And then this is really nice. I actually will be able to put that 30, make that a 1 pretty easily. Okay. All right, guys. And so let's go ahead and do that. Let's make this look a little bit nicer. So I'm going to go ahead and I'm going to multiply 136 or divide the 30 by 136 and put it back into row 3. And then let's do one other thing here also. I want to get a 0 in this term right here where that 4 is. So to get a 0 there, I'm going to multiply the second row by a negative 4, add it to the first row, and put it back into the first row. Or I could subtract them, that'd be fine too. But the reason that works out pretty well is because this one right here isn't going to get messed with because we got those zeros underneath it. That's the important thing, is you got to get these zeros right here before you start messing too much, or else you're going to be messing up those ones that you had got. Okay, so this is going to be 1. This will be 0. If I multiply that guy by a negative 4, let's see, let me do a little bit of work here. So I would have, oh, sorry, I think I just opened something. All right, so if I multiply that by, I'm going to have 4 plus, what, negative 16 elevenths, right? If I multiply that by a negative 4, no, that'll be positive. And then I'll actually have a 1. Isn't this fun? Watching me do arithmetic. I'm so sorry. I didn't mean to pick one that was this hard. Okay, so again, what am I doing? I'm multiplying row 2 by negative 4, so I'm going to multiply this term by negative 4 and then add it to this guy. So I have negative 1, excuse me, right? Plus, so negative 4 times negative 4 is a positive 16. 16 elevenths, well, you get it. And so if we add those together, that'd be 5 elevenths. So I get 5 elevenths here. And then with that 9, let's see what we get there. So I'm going to take that 16 elevenths, right, and multiply by negative 4 and add it to 9. So that'll be 9 minus 64 elevenths. And I don't really trust myself, so that'd be 99 minus 64, right, guys? 35 elevenths. Oh my goodness. All right. Bottom, I get 0, 0. I divide everything by 36. That becomes nice. I get 1 and 4. So we know Z is 4 right away. Okay, and I still have 0, 1, negative 4 11. So you're going to see this is going to actually work out really nice. It looks like it's not. But we're going to get there, I promise. Okay. All right. So last step here. I got to get zeros here. That's how I'm going to get that RREF form. Okay, and the nice thing is I have a 1 right here. So I can do this in 2 steps. And this is going to become, we're finally going to reap the benefits of all of our hard work here. So I'm going to take negative 5 elevenths times row 3 plus row 1 and put it back into row 1. I'm also going to take 4 elevenths times row 3 plus row 2 and put it back into row 2. And we will do some of these on the next class period. we'll do them on the fun sheet, right? So this was a little painful going through this. I think I'm going to be done after this, and we'll finish up everything on Tuesday. All right. I know these aren't going to change, right? Because I'm multiplying row 3 by stuff. And so because I have those zeros, nothing's going to change with those first 2 columns. Okay, so let's see in row 1. This I'm going to get a 0. That's why I did it, right? Okay, so if I take 4, this is going to work out lovely. 4 times a negative 5/11. That would be a negative, oh, I thought it was going to be lovely. It should have been. Negative 20/11 plus 35/11. That's not what I want to do, guys. I wonder if I made a mistake somewhere. Anyway, that's a, what, 15/11. We should have got something nicer than that. Hey guys, I'm so sorry about my software that just cut me off in the middle of it, and so I'm so sorry about the 2 videos. I'm about done with this example. I'm kind of over it. I bet you are too. I want to show you where I made a mistake. Oh, and it just made everything not work. So up here, oops, yeah. If you'll look at with me over here at this little 32 right here, this 32 is positive and this net 8 is negative. So I put a negative on the 144, which I should not have done. So this is going to change the sign here. And then when I multiply by that negative 11, oh man, I'm so sorry. My computer is really, really slow. Oh, there goes there again. Sorry about that. All right, guys. So, I don't know what's going on with my computer. We might have to just finish this one. So that negative, so this is a negative right here. This is a negative. Oops, let me show you. So this is a negative 4 right here. So then when I go through and do this, this will become a positive 20, maybe. Yeah, there we go. Oh, that makes me so much happier. And then I get 55/11. So this is 5. I still have a 1 and a negative 4 right here. So then when we go through and multiply by that 4/11, I'm going to get a 0 right here. But now notice here, I'm going to get a negative 16/11 plus 16/11, right? Which will give me a 0 here. Oh my goodness, I'm so glad that's over. I am so sorry to make you watch this like short video to finish this up. But the good thing is with all of this, we're going to eventually just use calculators. I promise. I promise our calculators will do it. But what is wonderful about getting it in this form, which this form now is what we call RREF, and we'll talk about this on Tuesday. I have a little box about it, and we'll write down the box on Tuesday because I'm kind of over it right now. But, right, what does this equation say? This equation says that this row says that x equals 5. What does the second row say? That y equals 0, and what does that third row say? That z equals negative 4. So it's actually a really great way to be able to see what the solutions are just by looking at it. Sorry for the 2-minute video. I can probably put these videos together. I'll try and do that, okay? All right, you guys, thanks. Sorry about that. I'll see you in class on Tuesday.